Section 1. The Soul of a Gadget. Unveiling the world of semiconductors. Electricity, the lifeblood of the modern world, courses through a vast network of materials. These materials dictate how freely electricity flows, shaping our technological landscape. At the heart of this intricate dance between matter and energy lies a fascinating class of materials, semiconductors. Neither perfect conductors nor staunch insulators, semiconductors occupy a unique middle ground, possessing an electrical conductivity that falls between these two extremes. Their ability to finely control the flow of electrical current underpins the digital revolution, making them the unsung heroes of our information age. From the smartphones in our pockets to the sophisticated computers powering scientific breakthroughs, semiconductors are the invisible engines driving countless technologies we rely on daily. Understanding semiconductors is akin to unlocking the secrets of modern electronics. It's about delving into the fascinating world of atoms and electrons, where tiny particles orchestrate the flow of information that shapes our world. Section 2. Between Two Worlds. How semiconductors bridge the gap. To grasp the essence of semiconductors, we must first understand their more straightforward counterparts, conductors and insulators. Conductors, like copper wires, readily allow electricity to flow through them. Their electrons, loosely bound to their atoms, are free to roll, creating an electric current with minimal resistance. Insulators, on the other hand, like the rubber coating on those same wires, fiercely resist the flow of electricity. Their electrons are tightly bound to their atoms, making it difficult for them to move and carry a current. Semiconductors, as their name suggests, fall somewhere in between. Their atomic structure sits at a crossroads, not as free-flowing as conductors nor as restrictive as insulators. This unique positioning gives semiconductors a remarkable property. Their ability to conduct electricity can be controlled. This control stems from their electrons' behavior, which can be influenced by external factors. Section 3. Silicon Valley's unsung hero, silicon and its kin. While many elements exhibit semiconducting properties, silicon reigns supreme in the world of electronics. Abundant and relatively easy to process, silicon has become the go-to material for manufacturing the chips powering our computers, smartphones, and countless other electronic devices. Its prevalence is so deeply ingrained in our technological landscape that it lent its name to the world's innovation hub, Silicon Valley. But silicon is not alone in its semiconducting prowess. Germanium, another element with similar properties, played a crucial role in the early days of semiconductor technology. The first transistors, the building blocks of modern electronics, were made from germanium. While silicon eventually surpassed germanium in widespread use due to its superior properties at room temperature, germanium continues to find applications in specialized electronic components and solar cells. Section 4. Temperature matters, heat and the dance of electrons. The electrical conductivity of a semiconductor is intricately linked to its temperature. As temperature rises, so too does the energy within the material. This increased energy translates into more vigorous vibrations of the atoms within the semiconductor lattice. These vibrations can sometimes be strong enough to dislodge electrons from their bonds, freeing them to move and contribute to electrical conductivity. Think of it like shaking a tree. A gentle shake might not dislodge any fruit, but a more vigorous shake will send apples tumbling down. Similarly, a small increase in temperature might not significantly affect a semiconductor's conductivity, but a larger temperature change can unleash a cascade of free electrons, dramatically increasing its ability to conduct electricity. Section 5. Doping. The alchemy of semiconductors. While temperature plays a significant role in modulating the conductivity of semiconductors, the real magic happens with doping. This process involves intentionally introducing impurities, atoms of different elements, into the pristine semiconductor lattice. These impurities, even in minuscule amounts, can profoundly alter the material's electrical properties. Imagine adding a single drop of red dye to a glass of water. The water doesn't turn completely red, but its color noticeably changes. Similarly, adding a tiny amount of impurities to a semiconductor doesn't fundamentally alter its composition, but it significantly influences its electrical behavior. Section 6. The future is etched. Semiconductors and our technological tomorrow. As we've journeyed through the world of semiconductors, we've uncovered the secrets behind their unique properties and the profound impact they have on our lives. These tiny specks of matter, carefully manipulated and assembled, form the bedrock of our digital age. From smartphones and laptops to medical devices and space exploration, semiconductors have become indispensable to countless aspects of modern society. The future of semiconductors promises even more exciting advancements. As researchers continue to push the boundaries of miniaturization and performance, we can expect to see even faster, more powerful, and energy-efficient devices. Quantum computing, a revolutionary paradigm that harnesses the bizarre laws of quantum mechanics, relies heavily on advancements in semiconductor technology. The journey of the semiconductor is a testament to human ingenuity, a story of our relentless pursuit of harnessing the power of the natural world to shape our technological destiny. As we venture further into the 21st century, one thing remains certain: the future will be etched in the language of semiconductors.